Example 11, Chapter 3, Fluid Mechanics. Air with the properties of R equals to 1070-760 and Cp equals to foot per force on slug, right? Foot. Shown in this picture, a flow study has shown in this picture through a turbine that produces 700 horsepower as shown here. So we can write W.S 700 horsepower, and there is also for the inlet and exit condition shown. Estimate the exit velocity V2. Estimate exit velocity V2 and the heat transfer Q to the system. The inlet and exit densities can be computed from the perfect as we have some properties for the inlet and outlet condition. For the inlet condition, D1 equals to 6 each and P1 equal to 150, T1 equals to 300 degree of Fahrenheit, and the velocity at section 1 is 100 foot on second. So we can calculate rho 1 equals to P1 on RT1, which is equals to slug foot cube, and rho 2 equals to P2 RT2. The P at R is 40 multiply to the R, which is, and multiply to the temperature Fahrenheit to Rankine. Is equals to a slide on a foot cube. With these properties, to calculate V2, we should write the energy equation obtained from the Reynolds transport theorem, which was Q minus W dot S at first. To calculate the velocity, we should write the M dot E in equals to rho 1 V1 A1. So M dot 1 equals to the multiply to velocity, which is 100, multiply to the area H2 foot slug on second. This is the m dot in, and from the conservation of mass we have dm on dt equals to 0, m dot 1 equals to m dot 2. So m dot 2 is rho 2 v2 a2 equals to, from this relation, v2 rho 2 from we calculate here multiply to a2, which is so we can calculate v2 equals to the 244 foot per second. So we now calculate the velocity at point 2. Now we can calculate the heat to the system Q. The relation for the energy equation from the lane of transporter was Q dot minus WS shaft or pump, W dot friction, W dot from the pressure equals to control value E rho dV plus sigma h1 plus out minus m dot E. In this problem, the friction force is 0. Pump also considered as the shaft force. A steady flow, the first term equals to 0 Q dot minus W dot S equals to, and the magnitude of the elevation of the flow is same, so these two parts are also equals to 0, equals to H1. And in the ideal gas we have H equals to m dot CP T. Anyway, we can write H at point 2, H2 plus multiply to m dot, which is rho VA, for example, for the point A, minus H1 rho, for example, 1 E1 A1. So Q dot equals to W dot S, which is our noun, plus H2 CPT M dot CPT1 T2 A1 M dot. With replacing the quantities of this parameter, we can calculate Q dot equals to BTU on